Welcome. I'm Bob Hazen from the Carnegie Institution's Geophysics Laboratory, and I welcome you to this session on data-driven discovery in mineralogy, crystallography, geochemistry, and petrology. I first want to give my very sincere gratitude to Rob Levinsky and Arkenstone. Rob has been a tremendous supporter of both the science and art of mineralogy. It's reflected, for example, in his Dallas Mineral Collecting Symposium. So he's a real important link between the scientific community and the collector community, and he did underwrite this session, so I thank him. This is a session on data-driven discovery, and the twin pillars of this are, first, as a community, our opportunity, and I think our responsibility to have open access, reliable data resources in mineralogy and geochemistry. A shout out to people like Bob Downs and to Jolyon Ralph, to Kirsten Leonard, people who have devoted years to building these data resources that we all use all the time. And the second thing, of course, is to develop analytical capabilities and visualization methods that allow us to interrogate our data in much higher dimension than just the typical XY plot. So today you're going to hear from two outstanding early career scientists. I think they reflect both the dynamism and the diversity of this community, the people who are driving this technique forward. First, we'll have Shauna Morrison, who will talk about data-driven discovery in mineralogy and crystallography, and then Simone Runyon from the University of Wyoming, and she's going to talk about data-driven discovery in petrology and geochemistry. So,
I have a pretty big, ambitious title here, Petrology and Geochemistry, the Future of Data-Driven Discovery. And I'm going to go ahead and put a caveat out there. I am neither a petrologist nor a geochemist. I am an economic geologist. So I come in and I take your data and I take your hypotheses and I say, how can I use this to try to understand how ore deposits form, how they've formed in the past? So be aware that's the bias I'm coming into this with. But of course, all of us, whether we are mineralogists, crystallographers, petrologists, geochemists, or the lowly jack-of-all-trades economic geologist, all of us are contributing in a very real and very important way to the evolution of Earth and our understanding of the evolution of Earth. And I think it's always important to take a step back and say, not only is the Earth evolving, but of course our science is as well. And of course, the 100th anniversary of MSA gives us a good opportunity to step back and put this into perspective. MSA, roughly the same age as the field of experimental petrology, the invention of X-ray diffraction, the first proposal, Wegener's first proposal of continental drift, though of course predating wide acceptance of plate tectonics by about 4 decades, a little bit older than the discovery of the neutron, and of course significantly older than the proposal of snowball Earth. Why am I mentioning snowball Earth? We'll come back to that. Just as an aside, this is a really fun game to play with relatives on their birthday. It doesn't necessarily make you popular, but it is interesting. So data, petrology and geochemistry, these are incredibly broad fields in the types of data that we're collecting, whether it's isotopes, ages, whole rock chemistry, and of course, we're really looking at tremendous scales. And we're thinking of scales both temporally and spatially. And already in the symposium, we've had incredible talks highlighting the importance of the micro, of the nanoscale data that we are collecting within these fields and how they contribute. You know, sometimes a couple microns can tell us about the whole world, maybe. And so just a few examples here. You know, we can step out from a single diamond and the compositions and the carbon isotopes and inclusions within a single diamond up through whole rock composition, trace and REE compositions of a given hand sample that we collected. And it can tell us about, you know, where that original parental magma may have crystallized in the crust, how deep, what was it pulling, do we have that europium anomaly? And of course, then we can go to the regional, the continental, the global scale. And every single one of us is contributing across these scales, and it's extremely important as we continue on and as we advance the sciences to try to link all of these scales, all of these spatial and temporal scales, and all of these various types of data in order to make more complex advances within the science. And of course, I'm preaching to the choir because all of you are following the literature. And it's impossible to ignore the presence of big data, the presence of data analytics, all of these incredible tools that, you know, Shauna just told us about. And it's actually very difficult now to find many papers that don't pull a little bit of information from some of these widely available data sets online. And I think importantly, many high-impact journals are now publishing articles that haven't produced any new data themselves, but are data mining. They're going to these databases, they are pulling those measurements that we are so good at making, and they're trying to reinterpret. They're advancing new hypotheses and new ideas without necessarily making any new measurements. So this may be a turning point in that idea of we're really good at measuring and really bad at interpreting. Now we can go back to those measurements and reinterpret with more and more available data. That being said, I don't want to belabor the point, but of course there are so many different databases out there that we should be taking advantage of. Just a handful that I'm particularly familiar with: NavDat, EarthChem, GeoRock. You can get whole rock chemistry, you can get age dates, you can get isotopic analyses, you can get mineral compositions. All of these things are becoming more and more available by the day, by the week, by the year, as I will show a little bit later. And of course, as we have more complex data and more types of data, again, we can go after more complex problems and we can try to push our questions deeper into geologic time. So thinking about scale, I'd like to start small, in my view of what small is, with the tourmaline group, and just a very small example of some of the things we can do with larger data sets. Tourmaline, I chose this because it's something I happen to always be interested in. Of course, it also happens to grace the MSA logo. Tourmaline is fascinating. The tourmaline group minerals are fascinating because they're stable across a wide range of geologic conditions in the crust, which is the world that I typically live in. So large range of pressures, large range of temperatures, acidities. As a result, of course, tourmaline can show up in pretty much any rock type. It's fairly stable across a wide range of compositions, meaning it tends to be a fairly common detrital grain within sedimentary rocks. We can form this directly from igneous melts. We can form this during metamorphism, and it can form directly from hydrothermal fluids. So you can find tourmaline in some way, shape, or fashion in pretty much any geologic environment in the crust. It also has the ability to take up a wide variety of major, minor, and trace elements, of course owing to the variable color that sort of makes it famous to, I think, a lot of collectors out there. So when we see something like these tourmaline group minerals that have such a wide variety of composition, we sort of think, what kind of patterns must be embedded in there? And I warned you, I'm an economic geologist, so the first thing that I think of, and many other people have thought of, is how can we use tourmaline composition as an exploration guide? If I'm looking for gold, if I'm looking for copper, can I zap a tourmaline crystal and find out if I'm going to hit it big or not? And back in '89, Clark et al. Published this paper in Economic Geology, Tourmaline Compositions as a Guide to Mineral Exploration. They had 130 analyses. It was major element composition only from 27 places around the world. And they limited their sampling to pegmatites, grisons, and granites. The whole goal of the program here was, can we use discriminant function analysis to try to determine if this specific tourmaline analysis came from a mineralized or a barren locality? And only looking at aluminum, iron, and magnesium, they were able to predict whether or not a tourmaline indicated an ore deposit was nearby with 85% accuracy. Stepping forward a little bit from those 130 analyses, now we can look at the composition of tourmaline in slightly more detail. So Henry and Dutroux, 2011, it should be over 8,800 fluorine-bearing tourmaline analyses compiled in order to help predict the exact chemistries that would allow a certain amount of fluorine to substitute into the tourmaline structure. Beyond that, so a much more recent study, 2017, not only are we now able to say, okay, a tourmaline is probably or probably not related to an ore deposit, but we can use the trace elements within that tourmaline as a proxy to better understand the composition and the evolution of an ore fluid in a given system. What this also means is someone who doesn't know anything but is torturing themselves in the Nevada desert in the summer happens to come across a rock. It happens to be a little bit interesting. It's dominated by phlogopite, but there's a little tiny band of, there's a little tiny band of tourmaline-rich rock in the center. I can pick that up. I can take this to the scope. I can look at spatial relationships between these two dominant phases, the tourmaline surrounded mainly by phlogopite. I can go to the microprobe and I can see there's at least two chemical distinct tourmaline phases here. With the help of Darby Dyer, we can figure out one of those is oxydravite or the other is just dravite. I can look at that same sort of crystal and find out that it has fluid inclusions that have a salt crystal in them. I can get hydrogen isotope compositions on that same crystal to figure out that this probably wasn't a magmatic hydrothermal fluid, and I can go and pull from work that other people have kindly compiled for me and figure out what sort of compositions and what sorts of fluids likely formed that tourmaline. And the reason that we can take this, we can take a field observation, we can pick up a sample and bring it into the lab and make these fairly large, grander scale interpretations, highlighted very nicely by Henry and Dutroux in 2018. There are so many publications out there now that we can pull from. We can pull from other people's detailed work and better put into context the things that we have found. And of course, over 2,500 publications, the vast majority coming in the last decade, and of course they will continue to increase. So thinking back to what Clark et al. In '89, is it mineralized or is it not? Here, now, we can use trace elements in tourmaline to try to model subduction zone fluids, to better understand the evolution of an ore-bearing system. So just one fun example. And of course, scaling. We're scaling up a little bit now, but starting with single mineral. The advent and accessibility of UPB geochronology and how this came in and massive compilations of detrital of igneous zircon ages across the world really helped to come in and cement the idea of the supercontinent cycles in Earth history. And of course, it's not good enough that we have all of this data saying how many supercontinents we think there were and when we think they existed. We have to add more data. So now people, and this is one of many, many examples of people who've come in and started to do these sorts of compilations. We've added our metamorphic facies. We're adding oxygen isotope data. We're adding seawater strontium curves. And we're doing this because, yeah, okay, so we have the supercontinents. Yeah, okay, so we know when they were. Not good enough. Now we want to get at these more complex questions. We're trying to understand when modern plate tectonics started to initiate, as an example. And within the supercontinent story, we're going to take a brief, sort of high-level look at a project that I've been lucky enough to be involved with, focusing on the supercontinent Rodina. So roughly 1.3 billion years old to about 900. I'm not going to argue with you on the details of that. Of course, there are many different proposed reconstructions for how the supercontinent was probably pieced together. I think the most commonly used now is the consensus model of Lee et al. 2008, but of course there are important additions and changes that have been made to this proposal since. And, whoops, sorry, there we go. And I think when I first got involved on this project, it had already been started, a paper had already been published by my colleague Chao Liu et al., who Shauna showed previously in her presentation. And I think he really started off simply wanting to look at what are the footprints? What are the geochemical footprints of the different supercontinents? And pulled very strongly from EarthChem to look at the geochemistry of igneous rocks across all of these different supercontinents. And what ended up happening was Rodina stuck out. He wasn't necessarily looking for any of these things to be different, but Rodina continuously distinguished itself in its igneous geochemistry. And again, pulling very heavily from EarthChem, but also supported by MinDat. And basically what you can see from Liu et al. 2017, really high zirconium, high niobium, and high yttrium consistently within Rodinian igneous rocks. And so the initial interpretations here, based off of this, were that there must have been significant within plate magmatism, sort of intracratonic or anorogenic. And this led to the idea that maybe there's a unique tectonic setting for the assembly of Rodina compared to these other supercontinents. I showed up, a year and a half later, and I was really intrigued by this idea because I'm a skeptic, and I was scientifically raised by skeptics to say, if something's different, it's probably wrong. And that's not a great way to approach science, but we all have our biases. And the idea was to sit down with Xiao, who was very open to discussion and reinterpretation, go back and look at the same elements from the same database. Not quite a full 2 years later. So these are the images I just showed you from Liu et al. 2017. This is what's coming out. The patterns are a little bit different. So you can see with zirconium here, we still have a distinct peak where we thought we had a distinct peak, but all of a sudden it has a really substantial neighbor. Similarly with yttrium, we have that same peak for rodinia, but again, there seems to be something sort of showing up at the tail end of Nuna that hadn't been present in the data sets 2 years prior. And again, niobium, still a peak, but significantly subdued. So when we just look at the geochemical data that we pull from these igneous rocks from EarthChem, we haven't negated any of the original interpretations. This still supports the idea there is probably significant within-plate magmatism, which still could be a different tectonic setting for the assembly of rodinia. But we decided to start looking a little bit broader. There are a lot of people working on these questions. I'm not even going to attempt to address any of that, that vast majority that's out there. But just to give you an idea of all the people working, all the different data, there are a lot of different authors out there who have suggested rodinia is distinct for one reason or another. These are just two examples. Sampson et al. 2018 went into the Grenville magmas, so one of the more famous orogenies associated with the assembly of rodinia, and showed through titanium and zircon thermometry that the Grenville granitoids tend to be extremely high temperature. So there's something a little bit different here. We're looking at things sort of 900 plus degrees C. Brown and Johnson, also 2018, compiled a range of different metamorphic facies through time and really suggested that there's generally very high metamorphic facies that are preserved from the Rodinian time, and that perhaps right after Rodinia, during the extension and breakup of that supercontinent, is when we first start to see really the appearance of lower grades of metamorphism. So there's a lot of different authors out there that say there's something different here. Again, back to my personal bias, what I wanted to pull in was the idea of let's look at the ore deposits that are associated with rodinia. And why do we care about ore deposits when we're trying to think of these large global questions? One of the main reasons is that many ore deposits only form in a specific tectonic environment or a range of specific tectonic settings. Many other ore deposits only form in association with a specific magma composition, which we can sort of then interpret is related to a specific tectonic setting. And in the past, many papers that have sort of touched on the ore endowment of rodinia have basically said it's barren. The entire supercontinent didn't have anything, there's nothing there. And there aren't too many databases that I'm aware of that actually list ore deposits. MinDat was a huge help that I pulled from. If anyone is aware of some that I am not, please let me know. Because what this ended up turning into was an incredibly massive literature search. And what I found at the end of that was, no, rodinia is not devoid of ore deposits. Of course, there's some economic enrichment that occurred during the life and times of rodinia. But there are really distinct patterns in what is present and what is absent. And basically what we found is that porphyry copper moly gold systems, epithermal orogenic gold, MVT, and VMS are really, really underrepresented from rodinia. On the flip side, there's an extremely high occurrence of pegmatites, carbonatites, kimberlites, and mafic or ultramafic nickel-copper PGE systems. So we step back and look at the tectonic settings in which those tend to form, and a pretty obvious pattern emerges. Porphyry copper gold moly, with a few exceptions, tend to form in subduction zones. Epithermal systems, given the name, you might have guessed, typically in the upper 1 kilometer of the Earth's surface, very commonly associated with subduction zones, also with some extensional zones. Orogenic gold, subduction zones. MVT, always hosted in platform carbonates, and VMS, most commonly associated in the back arc setting of a subduction zone. Whereas we look at the high occurrence ore deposits in Rodinia, these tend to be formed on stable craton or associated with intercratonal rifts. So what we're seeing reflected in our ore deposits is a very distinct presence of those things that were intercratonal and absence of things that form in subduction zones. Now, when we come back to that original interpretation, did Rodinia form from some sort of very different, very specific tectonic setting? That's one possibility. The ore deposits say, yeah, things were a little bit different. The temperatures of our granite suggest this is a little bit different. We have really high metamorphic gradients. Our geochemistry still suggests that the average magmatic composition is a little bit different. But then we take a step back also and look at what we have preserved of Rodinia today. So in gray are the cratons that would have been available. In green are the orogenies that we're pretty confident are linked to the formation of Rodinia. We don't have a lot of this thing left. And what that always comes back to is the idea of the potential of preservation potential influencing what we're looking at in the geologic record. That is my personal bias on looking at these data, is it's very easy to lose our epithermal systems in the upper kilometer. It's very easy to lose subduction zone related porphyry systems that tend to be emplaced in the upper 6 kilometers of the crust. When we look at a lot of the orogenies that are preserved, let's take the Grenville for example, many of these things are eroded down to 20, 25, 30 kilometers. That's deep enough even to go past the sort of the deepest known formation of orogenic gold. So there are different ways that we can explain these patterns that we've seen. Of course, I'm calling on, if this is the case, a pretty substantial loss of the supercontinent Rodinia. And there are some other people who have thought about this before, some thermochronologic data, some other studies that have also been published, really looking at extreme denudation after or during the breakup of Rodinia. And this study by DeLucia et al., 2017, saying a minimum of 6 kilometers in many places, of course, we know, again, from many of our orogenic belts, even deeper than that, which, of course, would have really important implications for the weathering and erosion, therefore the CO2 drawdown, and some sort of tangential potential suggestions that maybe this is related to the onset of snowball Earth. I promised I was going to come back to it, and I did. So with all that, of course, there's always going to be, no matter how much data we have, no matter how many types of data we have, there's always going to be the persistent challenge of understanding preservational bias in the rock record and making sure that we keep all of our interpretations in line with that possibility. There are also other challenges utilizing big data. We have to understand the source of our data. What was the question? What was the purpose of that project that collected all of the data that we're using? But that being said, there's more and more accessible data every single day, as I showed with that really distinct change in geochemical trends just for Rodinia. 2 years apart, the patterns changed really dramatically. It's important to push to get more data public. All of our little Excel spreadsheets don't do us any good if they're sitting on our laptop not being shared. And I think there's really important pushes being made in order to address how we synthesize various types of data. How do we take geochemical data, geophysical data, LiDAR data? How do we pull all of these things together in a way that they are usable and interconnected? That being said, I think we're going to be making progress. As Shauna highlighted, we have so many more tools now than we did a year ago, than 2 years ago. It's going to continue. And I think really this presents an opportunity to continue to address more complex problems further back into geologic history. So thank you very much.